Now you see, by extending these generating functions towards infinity and not truncating them, I was able to actually obtain this without resorting to any numerical methods or any computational tool. I was able to just derive it in an analytical way. Um, so it makes sense to actually not truncate generating functions when you are able to. However, sometimes it's not possible. For instance, what if the boxes are allowed no more than 10 balls? Now the question itself is imposing a limit on the number of balls that you can place in a box. So you cannot really extend your generating function towards infinity. You have to truncate it at x to power 10. And in this case, again, you gather x to power 2 terms. You get x to power 10 as earlier, times 1 plus x squared plus dot 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 up to x to power 8 to the power 5. Now, again, if you have a computing tool, you can expand this expression and obtain the result. But let's see how we can do this in an analytical way. So this is x to power 10. And this here, you see 1 plus x squared plus dot 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 plus x to power m actually is equal to 1 minus x to power m plus 1 divided by 1 minus x. So this expression here, 1 plus x plus up to x to the power 8 is in fact equal to 1 minus x to 9 divided by 1 minus x. So this is taken to the power 5. Therefore, I need the coefficient of x to power 10 in this function. And this function is simply 1 minus x to 9 to power 5. If I had just this, that would have been easy. But I also have 1 minus x to power minus 5. Okay, so since I have x to power 9 here, to obtain x to power 10, well, this will be a function involving all powers, 1 plus, well, let me just put a0 plus a1x plus a2x squared plus dot 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 something. Okay, so this function will turn out to be of this form, a polynomial of infinite order. But this one, this is a finite polynomial, finite degree. And you see, since I'm looking for the coefficient of x to power 10, this can contribute in x to power 9 or nothing at all. Because, well, if I actually include 2 of x to the power 9s, that would go to x to power 18, which exceeds this. So I don't need those. So either I'm not going to take any x from this first function, in which case I need to take the function, the x to the power 10 term from the second part, this one, or I take just one of the x to power 9s, and then from the second part, I need only the x term. Okay, so those are the only possibilities. Therefore, I can write them simply. This is 5 choose 0, because from this, I'm not choosing any x to power 9s. Minus 1 to power 0, minus 5 choose 10. This is simply the application of extended binomial theorem. Okay, so this part belongs to the coefficient of this, and this product belongs to the coefficient of x to power 10 in the second part, 1 minus x to power minus 5. Plus, to this configuration, I'm going to add the case where I'm selecting 1x to power 9 and 1x from the second part. So that is 5 choose 1 for just this one. And that is minus 1 to power 1 times minus 5 choose 1 for the second part. And if you apply the definition of extended binomial coefficient here again and arrange the terms. For instance, 5 choose 0 is 1, minus 1 to power 0 is also 1. So what this expression equals is 14 choose 10 minus 5 times 5 choose 1.